And I'll be presenting my lab for Physics 2212 involving everything about circuits. The purpose of this lab was to use principles of energy conservation and current conservation and predict the behavior of circuits containing resistors in series and parallel, also using multimeters to measure the actual values of conventional currents and potential differences in circuits, and finally examine the behavior of ohmic resistors and capacitors. Throughout this virtual experiment, first we were told to consider a simple series circuit of two 1.5 volt batteries, two resistors, and two ammeters as shown in the diagram to the top left. We were told to first predict the currents I1 and I2, and I predicted that these would be the same. So then we had to simulate said circuit. We connected the ammeters in a way that they read positive values, and then we connected the two batteries and recorded the ammeter readings for I1 and I2, and as you can tell, both currents were 0.02 amperes, which are equal to each other. We were then told to reverse the connections of one of the ammeters, and it read the exact same current backwards. Next, we had to replace one of the ammeters with a voltmeter, and when we added this, we were told to describe the readings of both of the two ammeters, of the ammeter and the voltmeter. So the voltmeter measured -3 volts from the batteries, and the ammeter measured 0 amperes at this point. And this is because the red probe is connected to the negative side of the circuit, and that is a positive probe, and then the black probe, which is a negative probe, is connected to the positive side of the circuit based on the current flow, and this has to do with the negative sign on the voltmeter. The ammeter was 0 because the voltmeter's high resistance created an open circuit preventing current flow. Then we had to remove the voltmeter from the circuit and close the circuit with a wire and use the voltmeter to measure the potential difference for each part of the path around the circuit. And as you can see in this next slide, we will measure the potential difference at each path and recorded the current at each one as well. So the first one was the two batteries, then we went to the wire only, then we did the first resistor, the second resistor, the wire once again, the ammeter, and then the last piece of wire. So after we did delta V at each one, they were all different based on the different positions, as you can tell, but however the round trip did equal 0 volts. Next, we were told to finish a graphical model that examined the potential versus position around the circuit, showing the various measured potential differences. So this is what I finished as my data based on each potential difference divided by that current, and that is what I plotted. So when I attached the voltmeter, I altered the circuit, and the reason it did not change is because the two meters are designed to measure different things and are connected differently in the circuit. Once I connected the voltmeter across the 100 ohm resistor again, I noted the ammeter reading was the same as before. Then I had to replace the voltmeter with an ammeter in parallel to the 100 ohm resistor. And what happened to this? The current became much larger, and I really think this is one of the errors in my lab today, because this would make the current incorrect and could actually damage the circuit. So I don't really think that was accurate. Next, we were told to calculate the resistance of each element, which is the potential difference over the current. So these are all of my values for each resistor, measured using the voltmeter, potential difference, and the currents measured at each part. Next, I needed to make an RC circuit by connecting batteries to a 10 ohm bulb and a capacitor in a series, and I observed the light at different times. I found that whenever I connected just the 10 ohm bulb to the batteries, the light was super bright. The bulb now had current flowing through it. And then when I disconnected the battery and connected the capacitor directly to the 10 ohm bulb, I found that the light began to dim. And this is because the current started to decrease. The capacitor was discharging. Then I had to measure the time it took in seconds for the capacitor to charge, and that was about almost 1 minute. It took about the same for it to discharge, and then for the 20 ohm light bulb, it was about half of the time. So what if you were doing this experiment in real life and used an actual ammeter instead of an ideal ammeter? What would be different? A real ammeter has a small but non-zero internal resistance, and when it is placed in a series, it adds more resistance to the circuit. So this would cause a slight voltage drop, lower recorded currents, and could possibly distort the behavior of the circuit. So what if we were doing this experiment in real life and use a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitors to reach full charge? The ideal circuit would include a real battery, a capacitor, and no resistors in series. The ideal prediction is that the capacitor would charge instantaneously and go from 0 volts to full voltage in 0 time. However, in real life, circuits always have resistance. Real capacitors can't handle infinite current, and real batteries can't supply infinite current. So in real life, the capacitor would charge very fast, but not instantaneously, most likely within a few hundred microseconds. Thank you.